a frozen horizon at the absolute edge of our solar system. It hangs in the perpetual twilight of the Kuiper Belt, a world that was supposed to be dead, inert, and locked in a deep freeze since the dawn of creation. The James Webb Space Telescope turned its massive gold-plated mirrors toward this lonely sphere, gathering infrared photons that had traveled for more than 4 hours through the vacuum. When the data packets reached the Space Telescope Science Institute, the analysts did not believe the readouts. The chemical and thermal signatures coming off the icy crust defied the fundamental laws of planetary thermodynamics. Something was moving beneath the nitrogen glaciers, altering the surface composition in real time and emitting an unexpected thermal pulse into the surrounding void. Stay with me. This is the real story of James Webb just saw something impossible on Pluto. The crisis within the planetary science community began on November 12, 2026, inside the high-security data processing facility at the Johns Hopkins University Applied Physics Laboratory. A small team of astronomers assembled to review the first deep-field infrared spectra of the Plutonian system captured by the telescope's mid-infrared instrument. This specific observation run was designed to map the distribution of complex organic molecules across the dark crimson expanse known as Cthulhu Macula. It was meant to be a routine baseline study to complement the aging data from the New Horizons flyby over a decade prior. Nobody expected this. As the raw telemetry was calibrated and translated into spectroscopic curves, the automated processing software flagged a series of sharp, unprecedented emission lines. The software indicated a sudden, intense spike in atmospheric pressure and temperature concentrated over a single geographic feature. The instrument detected a massive thermal rupture. To comprehend what the James Webb Space Telescope captured, you need to understand the sheer scale and extreme environment of this distant world. Pluto orbits the Sun at an average distance of nearly 6 billion kilometers, where sunlight is 300 times fainter than it is on Earth. At these distances, surface temperatures hover around 40 Kelvin, a state of cold so absolute that gases like nitrogen, carbon monoxide, and methane freeze solid into a brittle, glass-like crust. Within that frozen wasteland, the telescope captured something staggering. That is the temperature in Kelvin, detected within a localized thermal anomaly measuring less than 12 kilometers across inside the vast nitrogen ice plains of Sputnik Planitia. That translates to nearly minus 30 degrees Celsius. While that remains freezing by terrestrial standards, on Pluto it represents a catastrophic, blistering heat wave. It is an environment 200 degrees warmer than the surrounding terrain. This was not a gradual seasonal shift. The thermal plume was concentrated, violent, and actively discharging immense volumes of gas into the thin Plutonian atmosphere. The rate of atmospheric inflation was staggering. The telescope's instruments recorded a local atmospheric density increase of 400% in the span of just 48 hours, indicating an active, high-pressure eruption from an internal reservoir that shouldn't exist. The timeline of the investigation moved with intense urgency. On November 14, 2026, 2 days after the initial data packet arrived, Dr. Eris Thorne, a senior planetary geologist specializing in outer solar system volatiles, initiated an emergency verification protocol. He compared the Webb data with archive imagery from the New Horizons spacecraft captured in July 2015. The New Horizons data showed a completely placid, undisturbed ice sheet at those exact coordinates. This meant the anomaly was not an ancient, dormant geological feature. It was a brand new, highly energetic phenomenon that had broken through the crust within the last several months. On November 18, 2026, the research team engaged the International Planetary Science Network, bypassing traditional publication channels to issue an urgent request for ground-based stellar occultation observations. The goal was to use the light of distant stars passing behind Pluto to measure the exact composition of the newly erupted gas cloud. By November 22, 2026, the Keck Observatory in Hawaii shifted its observing schedule, aiming its adaptive optics system toward the Kuiper Belt. The independent data from Keck confirmed the Webb findings. The atmosphere of Pluto was actively changing, choked with complex, heavy hydrocarbons and a massive influx of pure neon gas. The presence of neon was the first major clue that something impossible was happening deep within the planet's interior. Neon is a noble gas that does not easily bond with other elements, and its presence in such high concentrations meant it was being dredged up from a deep primordial reservoir that had remained sealed since the formation of the solar system. As the weeks progressed, standard models of planetary cooling began to completely fall apart under the weight of the incoming data. On December 3, 2026, a controversial hypothesis emerged from a small working group at the Southwest Research Institute. The researchers proposed an extraordinary explanation. They argued that the James Webb Space Telescope had not witnessed a standard cryovolcanic eruption, but rather the rapid explosive collapse of a massive subterranean ocean pocket, driven by a runaway nuclear reaction within Pluto's rocky core. If these calculations are correct, the interior of Pluto is far from dead. It contains a highly concentrated slurry of radioactive isotopes, including potassium-40 and thorium, which have clustered together in a phenomenon known as a natural nuclear reactor. This subterranean engine is actively boiling the bottom of Pluto's ice mantle, creating pockets of superheated liquid water and gas that finally pressurize to the point of breaking through the crust. Everything we thought we understood about the thermal evolution of small icy bodies is wrong, one researcher noted during an emergency briefing. The discovery implies that small worlds at the edge of the solar system can maintain internal heat engines for billions of years longer than previously calculated, completely redefining where liquid water and potentially life could exist in the universe. The scientific community did not accept this radical nuclear hypothesis without intense pushback. Mainstream planetary scientists immediately sought a more conventional, less world-altering explanation for the Webb data. On December 9, 2026, a counter-analysis was put forward by the Planetary Science Department at the California Institute of Technology. The authors demonstrated that a localized orbital resonance with Pluto's largest moon, Charon, could create intense gravitational tidal flexing along deep fault lines within Sputnik Planitia. This mainstream counterpoint argues that the heat is generated purely by friction. They claim that as Charon pulls on Pluto's icy crust, the faults rub together, generating immense localized heat that melts the nitrogen ice sheet from below, creating a transient, short-lived thermal plume. It is not a nuclear core, it is a tectonic fracture, a seasonal release of built-up gravitational stress that will eventually freeze over once again. The implications of this discovery reach far beyond the orbit of Pluto itself. For decades, the outer solar system was viewed as a frozen museum, a pristine vault preserving the remnants of the solar nebula in a state of suspended animation. The New Horizons mission in 2015 provided our first close-up look at this vault, revealing a world of unexpected geographical diversity, with towering mountains of water ice and vast, smooth plains of shifting nitrogen. Yet even with those surprising revelations, the consensus remained that Pluto was a world in its twilight, slowly losing whatever residual warmth it possessed, gradually hardening into a completely inert sphere of ice and rock. The new data from the James Webb Space Telescope completely demolishes that narrative. The sheer energy required to produce a thermal anomaly of 240 Kelvin on a world where the ambient temperature is near absolute zero cannot be explained by simple passive cooling or minor seasonal adjustments. It requires an active, continuous, and highly concentrated power source. The discovery of this heat plume has forced scientists to re-examine the fundamental equations governing heat transport in icy bodies, revealing a massive gap in our understanding of how planetary mantles behave under extreme conditions. Consider the composition of the plume itself. The detection of pure neon gas alongside heavy hydrocarbons is a chemical signature that should not exist on the surface of a Kuiper Belt object. Neon is incredibly volatile. Its boiling point is a mere 24 Kelvin. On the surface of Pluto, any primordial neon should have escaped into space billions of years ago during the early chaotic phases of the solar system's formation. Its sudden appearance in a concentrated plume means it has been trapped under immense pressure, deep within the planet's interior, shielded from the vacuum of space by miles of solid ice until this catastrophic breach occurred. This chemical profile suggests that the internal structure of Pluto is far more complex and stratified than previously modeled. Instead of a simple core of silicates surrounded by a uniform mantle of water and nitrogen ice, Pluto appears to possess a highly differentiated interior with distinct chemical reservoirs that have remained isolated for eons. The mechanism that broke through these layers must have been violent enough to shatter a crust of water ice that, at 40 Kelvin, possesses the structural hardness of steel. This leads us to the critical turning point of the investigation. If the heat source is indeed tidal flexing, as the mainstream counter-analysis suggests, then the activity should be periodic, predictable, and tied directly to the orbital mechanics of the Pluto-Charon system. Charon is tidally locked to Pluto, meaning they always show the same face to each other, rotating around a common center of mass outside Pluto's physical surface. This unique binary configuration creates constant, subtle gravitational stresses, but standard orbital models indicated that these forces had reached an equilibrium billions of years ago. For tidal flexing to cause an eruption of this magnitude, something must have disrupted that orbital equilibrium. A recent impact by a large, undetected Kuiper Belt object, or a subtle gravitational interaction with a passing outer solar system body, could have nudged Pluto out of its stable alignment, reawakening the sleeping tectonic forces within its crust. If this is the case, the thermal plume is the first visible symptom of a planet-wide structural readjustment, a cosmic realignment that could trigger similar eruptions across other sectors of the planet. Conversely, if the radical nuclear hypothesis holds true, the implications are even more profound for the search for habitable environments in the deep universe. If a body as small and remote as Pluto can maintain an active, radioactively driven thermal engine capable of melting its interior, then the zone where liquid water can exist expands exponentially. We no longer need to look exclusively to the warm zones around stars or to the massive tidal systems of gas giants like Europa and Enceladus. Every icy moon, every large asteroid, and every lonely dwarf planet drifting through the interstellar dark could potentially harbor a warm, liquid ocean beneath its frozen exterior, protected from the harsh radiation of space by a miles-thick shield of ice. The research teams are currently working against the clock to analyze the secondary data packets from the telescope's near-infrared spectrograph. These files contain high-resolution spatial maps of the areas surrounding Sputnik Planitia, and early indications suggest that the thermal anomaly is expanding. The edges of the 12-kilometer rupture are showing signs of structural collapse, with massive blocks of water ice crust sliding into the newly formed sea of liquid nitrogen and hydrocarbons. The landscape of Pluto is being rewritten in real time before our eyes by forces we are still struggling to define. We must also consider the atmospheric consequences of this ongoing eruption. Pluto's atmosphere is incredibly tenuous, expanding when the planet is closer to the Sun, and collapsing, or freezing out onto the surface, as it moves away in its highly elliptical 248-year orbit. Pluto reached its closest point to the Sun in 1989 and has been steadily moving deeper into the cold of the outer solar system ever since. Scientists expected its atmosphere to be completely frozen out by now, turning into a thin frost on the surface. Instead, this single thermal event has injected more mass into the atmosphere in 48 hours than the planet typically retains during its entire orbital cycle. This massive influx of gas has created a localized greenhouse effect over the planet's northern hemisphere. The newly released methane and carbon monoxide are absorbing the faint sunlight, trapping what little heat reaches the planet and preventing the atmosphere from collapsing as predicted. This unexpected atmospheric resilience has completely upended the predictive models used by meteorologists and planetary scientists to study outer solar system climates, proving that internal planetary dynamics can entirely override the external influence of a star. The scientific community remains deeply divided, and the tension is palpable within the research centers. Every night, telescopes around the world and in orbit are directed toward that small, pale point of light, hunting for the next clue that will tip the scales of this debate. Is it a dying gasp of a world undergoing a brief, violent orbital hiccup? Or is it the awakening of a primordial nuclear engine that will keep Pluto active for millions of years to come? The answers are slow to emerge, separated by billions of miles of empty space and the mechanical limitations of our finest instruments. To understand how deep this mystery goes, we must examine the specific mechanics of the observation itself. The Space Telescope Science Institute operates the James Webb Space Telescope with extreme mathematical precision. The mid-infrared data was collected over an uninterrupted exposure time of 12 hours, 44 minutes, and 12 seconds. This was not a fleeting reflection or an artifact caused by cosmic rays striking the detector. The signal-to-noise ratio was exceptional, meaning the heat spike detected at Sputnik Planitia is one of the cleanest, most definitive planetary signals ever gathered from the outer solar system. When the data first materialized on the terminal screens in Baltimore, engineers initially suspected a calibration error with the instrument's cryocooler. The telescope itself must be kept below 7 Kelvin to detect mid-infrared light without its own heat interfering with the observations. A malfunction in the cooling loop could mimic an external thermal spike. However, diagnostic telemetry confirmed that the telescope's systems were operating at peak efficiency, perfectly chilled. The heat source was entirely external. It was coming directly from the surface coordinates of Pluto. The exact location of the eruption, Sputnik Planitia, complicates every existing theory. This region is a giant basin filled with convective cells of nitrogen ice. The ice behaves like a slow-motion fluid, boiling from the bottom up due to internal heat over cycles lasting hundreds of thousands of years. It is the youngest geological surface on the planet, almost entirely devoid of impact craters. The fact that the thermal rupture occurred precisely within this active convective zone implies that the basin is not just a passive repository for frozen gases, but a direct vent connected to a highly dynamic subterranean planetary interior. Geological modeling of the basin suggests that the ice sheet is anywhere from 3 to 10 kilometers thick. For a thermal plume to breach this barrier and register a temperature of 240 Kelvin at the surface, the column of ascending material must have been under immense hydrostatic pressure. This indicates that the subsurface reservoir is not merely melting, it is actively boiling and flashing into gas as it approaches the vacuum of space. The structural properties of nitrogen ice change drastically as it approaches its melting point of 63 Kelvin. At 240 Kelvin, nitrogen cannot exist as a solid or liquid at Pluto's atmospheric pressure. It becomes an explosive, expanding gas jet. This brings us back to the composition of the atmosphere before and after this event. Prior to the November 12th observation, Pluto's global atmospheric pressure was estimated to be roughly 10 microbars, which is 100,000th of Earth's atmospheric pressure at sea level. The sudden fourfold increase in local density means that an immense volume of volatile matter has been injected into the global wind patterns. This is creating localized supersonic winds radiating outward from Sputnik Planitia, tearing across the frozen mountain ranges of Aladrisi and Hilary Montes. These winds are carrying the heavy hydrocarbons and neon across the entire planet. Hydrocarbons like ethylene and acetylene, when exposed to cosmic rays and faint ultraviolet light from the sun, undergo a process called photolysis. This reaction breaks them down into complex organic compounds known as tholins. Tholins are responsible for the deep reddish-brown stains that cover Pluto's equatorial regions. The massive injection of new hydrocarbons from the thermal plume means that the global color palette of Pluto is about to undergo a dramatic, rapid acceleration of chemical darkening. As the surface darkens, it will absorb more solar radiation, triggering an unprecedented self-reinforcing climate cycle. Now look closer at the neon signal. In terrestrial laboratories, neon requires specific conditions to remain trapped within silicate rocks. It is usually found in deep planetary mantles preserved from the era of accretion. The detection of neon gas in the Plutonian plume provides the first direct confirmation that the eruption is drawing material from the very boundary layer where Pluto's icy mantle meets its dense rocky core. This is not a superficial, shallow crustal event. The plumbing system of this eruption extends down to the deepest, most fundamental layers of the planet's structure. This deep origin strongly reinforces the radical argument put forward by the Southwest Research Institute. A natural nuclear reactor, while sounding like science fiction, has historical precedent within our own solar system. 2 billion years ago, a natural nuclear fission reactor spontaneously activated in the Oklo region of Gabon, Africa. It operated for hundreds of thousands of years, sustained by specific concentrations of uranium isotopes and groundwater acting as a neutron moderator. If Pluto's rocky core accumulated a high density of heavy radioactive elements during its initial formation from the solar nebula, the conditions for a similar deep-seated nuclear engine have existed for billions of years. If such a nuclear engine activated or surged in power recently, the thermal wave would take millions of years to conduct through a solid rock core, but it would move rapidly if assisted by fluid convection. This implies that the boundary between Pluto's core and mantle is occupied by a layer of liquid water, a subterranean ocean kept alive by nuclear decay. The thermal plume captured by the James Webb Space Telescope is the manifestation of a massive thermal plume rising through this hidden ocean, melting the overhead ice sheets and venting into the void. The alternative explanation, the tidal flexing hypothesis from Caltech, requires an equally profound rethink of outer solar system history. For Charon to generate enough frictional heat through tidal forces to melt miles of ice, its orbit cannot be perfectly circular. Yet decades of precise astrometric measurements have shown that Charon's orbit has an eccentricity of essentially zero. It is a nearly perfect circle. For it to flex Pluto's crust now, a massive gravitational disturbance must have occurred within the last few years. Astronomers are now combing through the observation logs of wide-field survey telescopes, searching for any signs of a massive dark object that may have zipped through the outer solar system undetected.